Okay, so I'm going to whip through this bit quite easy because it's a very easy section. Okay, so this is a section called characters, and it's where you've got to look at how computers store text. So there are two, right, so first of all, I hope you understand that everything in a computer essentially boils down to binary and therefore a number. And so someone very intelligent some long time ago decided to invent something called ASCII, which is the American Standard Code for Information Interchange. Bit of a mouthful. American Standard Code for Information Interchange. There we go. It's quite a big old load of words. So what he did was, this person was, he gave every letter and symbol and a few other things a number. So a capital A is 65, a capital G is 71. They did capital letters first, I don't really know why. They started on these weird numbers. You might think it's weird they started on 65 and on 97, but actually if you look at the binary for 65, it's actually 01000001. And so that's why, because they'd already used some numbers for something else, so they couldn't start at 0 because these had already been used for something else. So they had to start at a certain number, and he thought, well, actually, it'd be quite good if it's just like 1, but like that. And then the lowercase version is that. So that's the uppercase version, that's the lowercase version. So it's actually not as insane as it looks, because this is what they look at to see the number, this last bit here, and then the letter or number, and then and so on and so forth. So there's not a lot they can ask you here that isn't logic. They normally tell you, you don't need to memorize these. They'll give you one of them. They might say capital, they might say, like, I don't know, M is 109. Please write the ASCII out for hello. And then you've got to go, right, okay, if M's 109, they probably wouldn't do something as crazy as that. Although hello isn't miles away. And you've got to work out that, H will be 5 letters before M. Checking. And then, and you work out the numbers. It's not very difficult. Okay, the only thing to remember is that capital letters and lowercase letters have different numbers. Space is 32, but you will not need to know these, you just need to understand them. But I'm pretty sure that question I just said will probably pop up because they love that question. But that's just common sense. Like, I don't think you even need to be taught that. If someone said A is 97, what is hello? I mean, it didn't even I wouldn't even need to be told I was talking about ASCII. I would just understand that it's likely that they go, the letters go sequentially. So the only other thing is to understand that this ASCII is, and this here is called a character set. So it's a set of characters, like it's a table with the characters and what they mean is. Now there's a problem with the ASCII one. So ASCII originally was 7 bits, so it only allowed up to 127 from 0, of course, so 120 different characters. They do have an extended ASCII, which has a larger character set, which is 8-bit, and in the exam they've said they're going to use an 8-bit ASCII, but they won't use any of the crazy symbols. But basically, just understand that this wasn't great for modern era, because obviously we've got a lot of other countries, a lot of other languages now, and so they invented something called a Unicode. And Unicode is a much larger character set. You've got a much larger, I think it's 65,000 characters. And so therefore, Unicode is just a more modern version. It is compatible with ASCII, so the numbers are the same to a point. So, like these are the same, and then they've added more, basically. It's not really rocket science. But Unicode is the more universal one, and the reason for that is for other languages being invented, more symbols in French and German and things like that, and, other symbols. So that's basically what a character set is, and that's all you need to know for this section. Right, now we're going to move on to 1.2.4 images. So hopefully you understand that an image, as always, is represented as binary. So basically they're represented as pixels, squares, and each one of those squares is a binary number. Okay, so we're going to look at two main keywords, and that is color depth and resolution. But I'm going to show you in my Excel demonstration because it's easier to understand this random image that I've drawn. So these are all pixels. Okay, so this image is 9 pixels wide and 9 pixels high. Okay, so the resolution of this is 9 times 9, because the resolution is how many pixels are in the image. That's what resolution is. So resolution, this one is going to be the height times the width, and it's in pixels, okay? So I do width times height in pixels, right? So that's what the resolution is, okay? Now, one of the things in the exam, it can ask about the effect of changing the resolution. Well, a higher resolution picture, because it has more pixels in it, is less likely to pixelate. Because if an image on the screen is 4 inches by 4 inches, and it has 8 billion pixels in it, those pixels have got to be absolutely tiny to fit into that 4 inch by 4 inch space. But if you only have 1,000 pixels in that 4 inch and 4 inch space, they've got to be much larger. And so that's why having a higher resolution is better, because it means that the pixels will have to be smaller and smaller. But of course, there's a payback. You don't get anything for free. And in this one, it will be the file size. As the resolution increases, the file size increases, but so does the quality of the image. So that's basically how it is. So when you hear about something being like 1080p, 4K, those are actually resolutions. Let me get up resolutions. Display resolutions. They're resolutions for a monitor, but they're the same thing. So if I bring some of these in, there's quite a few here. So these are the bits we're looking at. So like when you look at 1080p, the image for a 1080p video is actually 1920 by 1080. So actually it is 1920 by 1080. It's actually 2 million pixels in that image. Now strangely, and I think because they picked the lower number, I don't know why they say 1080 and not 1920, because in life they normally try to go, yeah, let's get the bigger number. So to be sneaky, you might think that 4K is actually this has gone up to like from 1080 to 4K. But actually on 4K, they sneakily use this number, which is the bigger one. So actually it's gone from 1920 to 4K. So 4K is 3840 by 2160. It's still a big gain, as you can see here. It is actually 4 times bigger, because obviously remember both the width and the height have doubled. So if you imagine that as like a square, let's get up a document here. So if you imagine I make a square that is, let's do it here, a width of 19.2, sorry, by 10.8. I didn't put 0.2, 19.2 by 10.8. Let's zoom in. So this is the ratio of 1920 by 1080. Well, actually, I need to have 4 of them to do the same, because both the width and the height is doubling. So if I just put that there, so that's 4 1920 by 1080s. Now if we do a image here and then do, what was the resolution? 38.4, 21.6, 38.4, bang, 21.6, bang, and then you can see quite clearly, I'll make it quite transparent, that you need 4 of them to fit in, and that's because the width doubles and the height. Okay, so the resolution is about how many pixels are in the image. Okay, but obviously, as you can see, you've got 2 million per frame for 1080, 8 million for 4K. So you can see, look, yeah, the quality's gone up, but so has the file size, because obviously every pixel needs to be stored. So that's what resolution is. Color depth is about how many bits we're allocating to each pixel. For example, if we only have a black and white image as here, we only need 2 options, 0 or 1, to represent each pixel. So we just need to use 1 bit of data to represent each pixel. And literally, if I actually made that into a byte size, killing that, that's now 8 by 8. That might be better. I'm just going to make the shape better. Oh, no, it doesn't matter. Who cares? So this is 8 by 8, okay? 8 pixels by 8 pixels. So each one of these is 1 byte. So you can see it just takes 1 byte of data to show this row. So we need 8 bytes, okay? 64. Width times height in pixels for the resolution, okay? Now, the file size is width times height times the bit depth. But of course, we only have a bit depth of 1 here because we're using 1 bit for each color. Right. What happens if we have a picture, and this is quite a common thought process. So I'm going to go through it here. I will go through it again in the questions bit. They might say a picture uses 5 colours. So there are 5 colours, okay? And the image is 300 by 200. So you see we've got a question here. And what you got to do is you first think, right, if I've got 5 options, 5 colours, I can label those colours 0 to 4, right? Because I only need to have 0 to 4 to represent the colours. Because colour 1 could be 0, right? So then I think, how do I write the number 4 in binary? And the number 4 in binary is 100. So to represent 5 colours, I in fact need 3 bits. This is quite a common tricky exam question where they give you the number of colours and you need to work out how many bits you would need. And what a lot of students do, and actually in this case it would matter, is they write out 5 in binary and go, you need 3 bits. And that's fine here because it's the same, but actually you don't need 5 because you can have 0 to 4. So 0 with 1 colour, then 1, then 2, then 3, then 4. So if we had a 5 colour image, we need 3 bits to represent it. So then we would do, our actual answer would be 300 times 200 times 3. And obviously it's going to convert it into stars, and then it's going to tell me that that is the answer. So that's how many bits would be needed to store an image with 300 by 200 for 3 bits for each one. Okay, so let's say by the way, modern pictures use 24 bits of data per pixel. This has been set now because they've done lots of studies that show the human eye can't see any better than that. And so 24 bits are allocated to each pixel. If this was a 24-bit image, it would take 1.5K to display that, and we would have that many color options available to us. We have 16.7 million, which is what 24 bits is. So if we had a color base 24, obviously we're only using 2 of the colors here, but we could have any color we wanted from the range of colors. So that's what color bit depth is. It's how many bits are allocated to each color. The more bit depth, the more color choices. But the more color choices, the larger the file size. Okay, I will go through a couple of example questions in my question section, and I think you should watch them because that will help. So we're nearly finished the color section. You might think that's it. We know everything. We've looked at the quality of the image. Increase in resolution means less pixelating. Increase in color depth means better colors. And if you want to know what it's like when you have a low color depth, I mean, I'm just going to show you a 8-bit image. What happens is when you get a low quality color depth is you get quite a lot of banding. Oh, here's a good one. So here, look. So this would be a high color depth and this is a low color depth. So because there just aren't enough colors to do a smooth transition between black and light, dark purple and light purple. So there's just not enough colors. So you get this banding. And you can see here, this is 8-bit and 10-bit. Look at the difference just those 2 extra bits give. Such a difference, no? But there you go. So that's what it is. Right, now last but not least, on the image section, there is something called the metadata. Now, when you've got to understand, when the computer has a file for an image, it's just loads of numbers, right? Zeros and ones. That's what the file is, just loads of numbers. So the computer doesn't know, like it's not always, it's not likely that the image is going to be a square. So how does it know which is when there's a new row? You know, how wide is the picture? How tall is the picture? What is the color bit depth? Like how does it know that that's how much each pixel is going to be? See? So basically, the metadata at the start of the file will tell it the color depth, the width, the height. I've got an actual example one here. And some other things, like so we've got the width and the height in pixels. We've got some other really random stuff. More modern things now, they keep loads of stuff in the metadata. Another really common one is like the GPS data. So you can actually have the location of the image was taken stored in the metadata. Another one is the date and time of the picture taken. So they're the main ones I would talk about. Ignore a lot of these weird ones. So you've got width and height and bit depth. You've got GPS data, you've got date and time, but there is quite a vast array of stuff now that can be put into the metadata because people like that. But, you know, it doesn't have to be there, and most of the main ones are the ones I've just listed. So that is images done. Right, I'm not going to talk too long on this topic because it's a topic that students normally understand very well. It's quite an easy topic. It's the last section, which is compression. So compression is the act of using an algorithm to reduce the size of a file. So you can use some clever algorithms to reduce the size of a file. One of them we've done before is run length encoding. So if I just show some run length encoding, but it is the easiest algorithm in the world ever. So let's say we had AAA, BB, CDD. So that could be represented as 3A, 7B, and then 3D, because there are 3A's, they're followed by 7B's, followed by 3D's. So run length encoding is an example of a compression. Okay, and so obviously if we look at this data, we go, right, okay, the computer goes 3A's, AAA, 7B's, 1, 2, 3, 4, 5, 6, 7, 3D's, 1, 2, 3. And you can see that I've got the files back exactly as it was before. And this can be done with binary data, other numbers, words, but that's a version of encoding called run length encoding. Quite an easy one to understand, really. Don't need 150 examples of that because it's quite easy. So in compression, so the whole idea is to compress the file down. The only slight downside to compressing a file is that it does take some processing to decompress it. It isn't free, but not that bad. So there are two types, lossy and lossless. Okay, lossy compression, which is the compression that normally gives the best compression rate. So that means it makes the smallest file afterwards. Lossy compression changes the file forever. So once it's compressed, when it's decompressed, it's not the same. So some quality somewhere is lost. This is always used really for media files, pictures, videos. An example would be MP3s or any video codecs, because think about it, as long as the image looks 99.9% the same as the original, it doesn't matter, especially if you've got it down to sort of 10% of the file size. If it wasn't for video compression, videos wouldn't be a thing, because they need to be compressed really to be able to be transmitted online. And so there are lots of clever techniques to try and take data out or compress it where the human eye can't see it as much. And there are other clever ways they do it. But all you need to know is that lossy change the file forever. So when you decompress it, it is not the same. Quality has been lost. Okay, and it's only used for media. Lossless, which is actually what we just did here. This was a lossless compression. This file is exactly the same. And if I did this 1 billion times, as long as there were no errors in the algorithm, this would be the same. If I kept going back and forth, I can compress and decompress this forever. And in theory, it would be the same unless there was some sort of coding error, but that's obviously not part of this. So lossless compression compresses it and doesn't lose any quality. The file afterwards is binarily, if that's even a word, exactly the same when it's decompressed. However, you do normally get a significantly less amount of compression because that's just the way life is. So this is used when quality is either extremely important, so it could be used in some really high level medical stuff where you really can't afford any quality and loss of a scan or something like that. Or it's used for EXEs. You can't have an executable file on the computer, suddenly have a randomly different bit of binary. It would be terrible. Things like Word documents. You can't have most of the letters be correct, or an Excel file where some of your math is correct, but you've now lost £1 million, but it was nearly the same. So lossless compression is used when on things that you can't afford to have any changes to, and so anything that isn't media, really. Examples of that are zip and rar, quite common compression formats. But yes, so that's compression. There's not a hell of a lot to learn with that, so I'm just going to keep it nice and short.